Welcome, everybody. We will be getting started here shortly. Naoki Nagai, thank you for being our DJ for today. Can you please start the recording? Great, thank you. So we'll just give it a minute or so, and then we will get started. Thank you, everybody, for joining us. We'll get started shortly. I'm seeing the number of participants go up. Reminder that today's session is being recorded. Okay, I think we should get the party started. So again, welcome everybody to today's session on carbon negative technology innovations fighting climate change. This virtual gathering is being recorded. I am Veronica Rocha representing PICHTR. My co-host today is David James from the OIST Foundation, and our esteemed DJ is Naoki Nagai, also representing PICHTR. So to get us started, I'm going to ask everybody to please introduce yourself. So in the chat, if you can please enter two things. One, where are you calling from? And then second, how did you hear about this webinar? And then I'm gonna ask Naoki if he can please read off some of the responses that we're getting from the audience.
Oh, Honolulu, we have participant from Honolulu. Arizona. Tokyo. Yeah, he heard from David about the series. Waimea from the email list. ASU Office of Sustainability. Maui, Florida. OIST Foundation.
Wonderful. Okay, let's try out another feature. If we can please go to the Q&A and please input what questions are you hoping will be answered by today's discussion. And just as a friendly reminder, at any time during today's webinar, please enter your questions into the Q&A. We will have about 30 minutes at the end. That's our goal, at least, to have an interactive discussion with our panelists today and address as many as your questions as possible. All right. Well, I think we should go on to discuss, provide an overview on today's discussion. So I will be doing just a quick introduction on PICHTR's Climate Adaptation Collective, followed by David James, who's going to give us an overview on OIST and the OIST Foundation. Then we'll provide a quick backdrop on today's discussion, followed by 3 excellent panel presentations. And at the end, we will do about 30 minutes, give and take, of a group discussion. And again, friendly reminder, please enter your questions into the Q&A at any time. Climate Adaptation Collective is PICHTR's newest initiative. The focus of this initiative is on climate change adaptation, in particular pertaining to capacity building and advocacy. The word collective refers to the collection of related challenges, opportunities, and also people that are committed to making a meaningful difference in climate change adaptation. David, can I have you talk a bit about the OIST Foundation?
Sure. Thank you so much. And thanks everyone for joining us. And thanks to the panelists as well. The OIST Foundation is a US-based 501c3 nonprofit that began a year ago. And we support scientific breakthroughs, innovation, and the sustainable development of Okinawa through OIST. And for those of you who don't know, OIST is a 10-year-old, so still quite young, university in Okinawa, the Okinawa Institute of Science and Technology Graduate University. We offer a 5-year PhD program in the sciences, and we're completely interdisciplinary. We're also trying to really promote innovation in Okinawa. And the last thing I'll say is we have a very strong focus on climate, environmental research, and alternative energy, and are extremely pleased to be partnering with PICHTR. Thank you.
Thank you, David. So happy that you're here and that we can partner with you on today's event. We are also very grateful for our sponsors. Today's webinar is made possible thanks to our sponsors, Hawaiian Electric and the Consulate General of Japan in Honolulu. I would like to offer you a brief backdrop on today's discussion on carbon negative technology innovations that are fighting climate change. So the question that I want to address is climate change getting better? And without spoiling it for you, unfortunately, the answer is no. Naoki, can I please have you transition to the video from the UN Environmental Program?
This year's lockdowns have caused emissions to fall dramatically, but emissions are already rising again, in some places surpassing pre-COVID levels.
Ecosystems are collapsing. Our life support systems are being destroyed.
I invite everybody from the audience to take a look at the UN's Environmental Program's progress report for 2020. One of the big themes of this report is that if international country commitments are achieved, there's still a significant gap to get us to only 1.5 degrees C increase in global surface temperature. And unfortunately, we are tracking at this point with the given commitments closer to 3.2 degrees C increase, which is frankly catastrophic. So transitioning over to the topic of today's conversation, it is absolutely imperative that as a world community, we reduce carbon dioxide emissions. And today we will be discussing 3 technologies that reduce CO2 emissions in the atmosphere. The first one is on CO2 repurposing, and we're going to be hearing from PICHTR. The second is CO2 sequestration through enhanced floral activity through seagrass and kelps. We're going to be hearing from Concrete. And then thirdly, switching from burning fossil fuel to renewable energy through the next generation solar cells. And this we're going to be hearing from OIST. PICHTR and Concrete also support climate change adaptation. And it'll be super interesting to hear from both of our speakers today. So I would like to turn it over to David James to please introduce our three esteemed speakers.
Thank you so much. It's a real pleasure to introduce you to our speakers today. Let me give you just a very brief background on them. First, we have with us Christy Gamble, who is joining us from Saskatchewan, Canada. This is quite an international group. She is Senior Director of Sustainability for CarbonCure Technologies. And CarbonCure's mission is to reduce 500 megatons of annual carbon emissions from the cement and concrete industry. CarbonCure manufactures a technology that enables concrete providers to utilize post-industrial carbon dioxide in their manufacturing processes in order to achieve significant embodied carbon reductions without compromising concrete quality. So we're very excited that she is with us. Next, let me introduce to you Dr. Shimrit Prokol-Finkel, joining us from Israel. She is the co-founder and CEO of eConcrete Tech, a world leader in bioenhancing concrete technologies, which was chosen as one of Time Magazine's 100 best inventions in 2019. eConcrete helps reduce the ecological footprint of coastal and marine infrastructure projects by bringing concrete structures like seawalls, breakwaters, and piers to life. Shimrit has over 20 years of experience in marine biology and ecology in over 30 countries, specializing in ecological enhancement of urban marine habitats, and is considered a world expert in ecological engineering. So thank you to you, Shimrit, for joining us. And last but certainly not least, we have Dr. Yabing Ki, who is joining us from Okinawa. So Saskatchewan, Israel, and Okinawa represented here, of course, and also myself in New York and Veronica and her colleagues in Hawaii. But Yabing Ki is professor. He is a professor at the Okinawa Institute of Science and Technology Graduate University in Japan and is a fellow of the Royal Society of Chemistry. He received his bachelor's, master's, and PhD from Nanjing University, and also studied at, his undergrad from Nanjing University, but also his other degrees from Hong Kong University of Science and Technology and PhD from University of California, Berkeley. His research interests include surface sciences, perovskite solar cells, energy materials, and organic electronics. So we're very excited to have all three of you here with us, and I'll now turn it over to Christy.
Well, thank you, David. I'll share my screen here. I would, while I'm getting set up here, I would first like to thank the wonderful people at the Elemental Accelerator for making this possible. They're a group based in Hawaii that has accelerated CarbonCure's adoption in the state of Hawaii and provided this opportunity. So just want to confirm, David, do you see my screen?
Yes.
Thank you very much. All right, well, as David mentioned, my name is Christy Gamble. I am the Senior Director of Sustainability with CarbonCure. I am quite certain I get to claim the prize for a presenter coming from the coldest climate. It is -24 Fahrenheit where I live right now as we speak, and that's not including wind chill. So really wishing I was back in Hawaii at the moment. That would be lovely. But in any case, I'm here to talk to you today about CarbonCure's mission to reduce the carbon footprint of concrete through CO2 utilization. Now, first of all, just to set the stage, did you know that embodied carbon is expected to account for about 50% of the carbon footprint of new construction? So embodied carbon refers to the carbon footprint of a building before the lights are turned on for the first time. This is the carbon that comes from the manufacturing of building materials and construction of the building itself. Traditionally, when architects and owners and designers were talking about reducing the carbon footprint of buildings, they were often talking about the operational emissions. So the carbon that comes from the heating and cooling systems, the lighting and energy that happens in a building. But there's been a lot of innovation in that space, relatively little innovation in the space of embodied carbon. And as a result of that, it's becoming a much larger portion of the overall carbon footprint of a building. So this is resulting in greater urgency to address this concept. Now, concrete is the most abundant man-made material in the world. In fact, it's the second most abundant material, period, after water. So because of its sheer abundance, concrete happens to have a significant impact on carbon emissions. And in fact, cement production, which is cement is the key ingredient used in concrete. Cement production is responsible for about 7% of the world's CO2 emissions. So with that all said, CarbonCure's mission is to reduce 500 megatons, so 500 million tons of carbon emissions annually by the year 2030. So this would be equivalent to taking over 100 million cars off the road each year. And how we do this is through our suite of technologies that utilize CO2 in concrete production. CarbonCure's technology beneficially repurposes carbon dioxide to reduce the carbon footprint of concrete without compromising concrete's performance. So I'll explain a little bit about how the technology works and where we're available and what that means. CarbonCure's technology is operating in about 300 plus concrete plants across primarily North America, but parts of the world as well. And it's really exciting to see participants from Malaysia and Japan, which are among the markets that we anticipate we will be available in the near future. Right now, the majority of our production occurs within the United States. We are a Canadian company, but we've had a lot of traction in the US. To date, about 8.5 million cubic yards of concrete have been used in a wide range of construction projects. This has resulted in over 100,000 tons of CO2 saved, and it is compliant with existing codes and standards. So specifically, for those who are familiar, it's ASTM C494 Type S. What this means is that it's available for a wide range of applications for concrete production. And of course, as you'll notice on the bottom left there, the state of Hawaii, we have two wonderful partners within the state of Hawaii, Island Ready Mix and HC&D, who are concrete producers providing concrete made with CarbonCure's technology to the state, specifically in Oahu. So how this works, CarbonCure is delivering a precise dosage of captured CO2 into concrete. What's happening is the CO2 is collected from industrial emitters. Now, CarbonCure does not collect the CO2. We work with third-party industrial gas suppliers who have capture technologies that capture CO2 from typically fertilizer plants and ethanol plants. They purify that CO2 and deliver it to the market. Turns out it's a huge industry for this captured CO2 because it's used in carbonated beverages. So soda, Coca-Cola, Pepsi, beer, that's all CO2 that came from a fertilizer plant originally, which I know sounds delicious. So one thing that's important to note is that this capture process already exists, but it's not currently environmentally friendly because the CO2 remains a gas and goes back into the atmosphere. CarbonCure is tapping into that existing CO2 supply source. We introduce it into concrete and chemically convert it to a mineral and get rid of it. So going back to how that works, the CO2 is delivered to concrete plants by these gas suppliers and stored in pressurized tanks. So this pressurized tank is a permanent installation at every concrete plant where technology is stored. The CO2 supplier comes by on a regular basis and refills that tank. CarbonCure's technology then delivers a precise automated dosage of the CO2 into the concrete. So if anyone happens to be familiar with how concrete is being made, it's just like another admixture that's used in concrete. So it's not interrupting the normal procedures that happen at any given concrete plant. It's essentially another ingredient that goes into the concrete mix. But what happens when that CO2 is introduced into the concrete, a chemical reaction occurs where the CO2 reacts with cement that's in the concrete and turns into a mineral. So this chemical reaction, it's a little more complicated than what we show here, but just simplifying it, cement plus CO2 react together in the presence of water to convert into calcium carbonate, which is limestone. So it just so happens that concrete has this unique property where it's able to convert CO2 into something else, which in this case is limestone, which is a mineral. So we're taking what would be pollution, introduce it into concrete, turn it into a mineral, get rid of it forever. It will never re-release into the atmosphere because that CO2 no longer exists. It's being turned into a rock, and that rock is embedded in the concrete. But this also results in additional benefits. The mineral that's resulting from this reaction is a nano-sized calcium carbonate mineral. This nanomaterial binds to the outside of cement grains, increases the surface area for cement, creates more surface area for the hydration reaction, which gives concrete its strength to bind to. And ultimately, this improves the concrete strength. So this allows concrete producers to in turn use less cement while achieving the same strength as they had before. Ultimately, concrete that's delivered to construction sites meets the same strength and other quality performance criteria, but with less cement and less carbon. This whole process has a neutral impact on the fresh and hardened properties of concrete. So anything that a general contractor or structural engineer or an architect or building owner would be concerned about, these properties are all maintained. It is the same concrete with less carbon. How much less carbon? It's about 20 to 35 pounds of CO2 saved per cubic yard of concrete. This number really varies depending on the mixed designs. There's a bunch of different kinds of ways of mixed designs to make concrete, whether you want low strength, high strength, and therefore different amounts of CO2 that can be saved. If a rough average is, it's about 25 pounds of CO2 per cubic yard. And this really can add up on a case-by-case scenario. So a number of examples of projects that have been delivered across the country. A lot of the concrete, the 8.5 million cubic yards of concrete we've supplied, a lot of that is going to driveways in rural Indiana. So it's a lot of everyday concrete, but also a lot of pretty fun construction projects as well. So some of the key ones to point out here, if you look at the bottom right, for example, is in Arlington, Virginia, we've recently started construction on the Amazon headquarters. Which is expected to save about 2.5 million pounds of CO2, which is significant. And perhaps one of my most personal favorite projects is the Kapolei Interchange in Honolulu, Hawaii. So I did have the pleasure of visiting Hawaii 2 years ago. Coincidentally, it happened to be the only work trip where my husband and kids came along, figure that. And there we were able to meet with a number of wonderful people on the islands, including the Hawaii Department of Transportation, who demonstrated the use of CarbonCure concrete in concrete paving and has now incorporated CarbonCure, concrete made with CO2 into its standard design specifications. So just to comment on the overall theme of today's presentation, the future of carbon utilization, there are many fascinating and amazing technologies that are developing in the space of carbon capture. This is an example of direct air capture, so not a CarbonCure innovation by any stretch, but a technology that captures CO2 from the atmosphere. The question that needs to be asked in any kind of carbon capture scenario is, what do you then do with the carbon once it's been captured? Storage is one of the key challenges, and being able to store carbon is a great solution when it is available and economically feasible. An even better solution is to utilize carbon for beneficial purposes, such as concrete production. And so that this concept of carbon utilization is in fact expected to be a $1 trillion industry by the year 2030. So we're very humble and fortunate to be able to lead that industry at this moment and really encourage further carbon utilization across various applications. So with that, that's the conclusion of my formal presentation. I'll be really happy to take questions afterwards. And I would just encourage everyone to build for the future and to build with CarbonCure. And please feel free to see my contact information that reach out.
Thank you, Christy, for that excellent presentation and overview on your technology as well as a bit of the industry. I would like to now turn it over to Shimrit to discuss eConcrete and their projects.
Great, thank you very much. And that was an excellent opening for my theme, which also focuses on different ways of burying CO2 into concrete in different ways. In my case, as my background indicated, I'm a marine biologist, I'm a diver, and we're looking at this problem with a solution that actually taps into natural resources and natural processes, including the growth of marine flora and fauna. So we already covered a little bit of the introduction here, but I will recap a little bit and focus us on the problem that leads me to the coastal and marine environment. About half of us live along the coastline, and we are faced with growing human population growth and mega cities and ports and marinas, and all of these are basically translated into a lot of concrete structures along the coastline. And about 70% of everything we build in the coastal and marine environment today is made of concrete. And we already heard a bit about potential advantages in using CO2 within concrete, but let's say from a biological perspective, concrete is not the ideal material for marine life to thrive on at the moment. It's because of three main problems. The concrete chemistry is very harsh, especially the cement of the concrete is very harsh for marine life. And also some of the additives that are being placed into concrete are detrimental for larvae of corals and oysters and the like. On top of the chemical properties, there's also a problem of lack of design and very smooth surface area, which is typical to the industry. All of this doesn't allow for shelter or any niches for organisms. And therefore, what we're seeing on concrete structures in the water is very low diversity and a lot of nuisance and invasive species. So these are kind of the problems that are associated with concrete in the marine environment from my perspective. And we already talked about the fact that it's a very vastly used material and it's a very carbon intensive material as an industry. One of the other problems that is really linked to this is the issue of climate change is creating a vicious circle. As we're seeing climate change impact, we're seeing stronger storms coming in more frequently, and we're seeing sea level rise that are inflicting danger to communities and assets along the coastline. And that really drives us to keep on building concrete defenses, building seawalls, bringing breakwaters, coastal defense schemes. And these are taking the place of beautiful, highly productive, natural coastal ecosystems like coral reefs or mangroves or oyster beds, which are, by the way, not only super productive and super diverse, they're also the natural defenses of our coastlines, again, creating this vicious circle. And that's really what inspired myself and my co-founder to really innovate and come up with a win-win solution that helps us use concrete, but use it wisely and use it responsibly while also sustaining marine life. So we took each of those problem areas that I described, the composition, the lack of surface texture, and the lack of three-dimensional design, and we looked at it from a biomimetic approach, and we found an innovation. So the first level is the concrete composition. We've basically developed a new additive into the concrete that is made nearly entirely of byproducts and therefore is very low in carbon. And once you add it to kind of a standard marine gray concrete mix, it neutralizes some of those negative effects on marine life, and it enables us to have a thriving community. Again, similarly to CarbonCure, e-concrete doesn't interfere with the strength or operational capacity of the concrete. If anything, we're actually slightly increasing those parameters for marine construction, and therefore the engineers can use the concrete feeling safe and sound, but also feeling that the marine ecosystem is doing much better. With respect to the surface texture, we're again looking at nature. We're using biomimicry and we're looking at surfaces that exist and kind of enhance marine life, like the shell of an oyster or polyps of the coral. And we're basically imprinting these onto our designs and our products. And finally, we're actually looking at habitats like water retaining features of rock pool, or even the mangrove system roots, and we're mimicking that into the design of the seawall or armor block or whatnot. So these three components work together to really bring the concrete to life. And that's where we're looking at a completely different angle of utilizing concrete into a mechanism that draws CO2, because a lot of the life that you're seeing growing on the concrete is actually organisms that use CO2 from the water to make their calcium carbonate skeleton. And that really helps us being in line with many of the UN Sustainable Development Goals and really help transform this industry to something that's much more holistic. So what are the advantages of using e-concrete? And that's kind of the main reason we developed the technology. So first of all, how can we increase biodiversity? create better and more diverse ecological niches, create nursing ground, improve the ecosystem services, and even the water quality around the infrastructure because we have a lot more filter feeders. We're even able to reduce the dominance of invasive species and also get a much more aesthetic infrastructure. And it's very important when you have communities just on the waterfront to have accessibility to urban marine nature. So this is really the core advantages that we designed the technology for. But as we started working with the technology, we realized that there are additional advantages. So the life that develops on the concrete is actually creating protection from erosion, from scour, and even from chemical attacks onto the concrete and onto the rebar in a process called bioprotection. And that's also a type of bioutilization where the life that develops on the concrete much more effectively is actually increasing its performance. And even in the long run, we can look at better longevity of the infrastructure and reduce maintenance cost. And finally, the angle of the lowering of the carbon footprint. So we actually, the component on the admix level or the dry concrete is quite modest. It's nowhere in the scale of CarbonCure. And that's where I can say that I'm really hopeful that in the future, we can even collaborate with CarbonCure technology and get a very full low carbon solution. But our admix, as I mentioned, that is designed for biology is actually almost carbon neutral, made of byproducts. It's non-hazardous, and it's representing about 10% of the cementitious materials. And we also use it in vast quantities with slag cement, which is another byproduct of steel industries. So overall, we can have quite a low carbon footprint at the level of, X factory. But this is where EconCrete's real contribution starts with the enhancement of marine life that are actually doing carbon sequestration. So one component, which is actually quite significant, is through the organisms that are doing calcification. These are the oysters, the tube worms, the coralline algae, the corals. All of these organisms are uptaking CO2 from the water and making it into calcium carbonate. And it is quite a delicate process, but it will happen throughout miles and miles of concrete structures. And it will not only happen 1 year, it will happen throughout the lifespan of the infrastructure. And the design life for these structures like breakwaters and pier piles is between 60 to 120 years. So we can have quite a meaningful contribution in a natural process, in a natural way. And finally, also photosynthesis. So we're enhancing the growth of canopy algae and different types of algae on the concrete. And with that, we're also adding another kind of pocket of carbon offsetting. So how do we actually utilize the technology? We use it in different ways in marine construction and coastal construction. And this is really just a couple of examples, but the technology can be applied to any concrete in the marine and coastal environment. This is actually a product that we designed and won the Biomimicry Design Challenge, which is a rock pool that is basically an armor block to use for scar protection for the beach. We're doing different seawall designs, marine mattresses that are used for protecting shorelines from erosion and also protecting offshore energy facilities from different scouring. We can do retrofit of pier piles. This is a new single layer armor that we've designed for the Port of San Diego. It's just now going into construction and different armor block designs. And I think the beauty is that this is starting to scale. So we're quite a young company, but we are already seeing that our technology is being integrated to large schemes, including a breakwater scheme in the state of New York that's actually going to protect the lives of citizens that have been threatened by storms like Superstorm Sandy. And this is where I want to touch another angle of the technology. We are helping create an on-site mitigation tool by habitat creation. And that can make the technology even cash positive, RI positive, because we're taking some of the mitigation penalties down. But this only happens in countries that have a strong regulation. So I would urge countries to go through mitigation strategies that are looking at climate adaptation as well. So this is where we're at, mostly US, Europe, one activity in Hong Kong, and we were hoping to really expand our activity. We're working with port authorities, with municipalities, with governments, and private sector to give a more holistic and sustainable approach to coastal and marine construction. We hope this to be the norm and for every project to actually provide a suite of biological advantages like biodiversity, better water quality, and a stronger carbon sink, but also to help the project be more effective. So to help with the permitting, to reduce mitigation costs, and to help have an overall low maintenance project. So that's our win-win. And I'm very happy to be sharing this with you, and I'm happy to take any questions later.
Thank you so much, Shimrit, for that excellent presentation.
Thank you.
Yeah, next I would like to turn it over to Yibing to talk to us about next generation solar cells that he has been working on. So I'm sorry, not Shimrit, Yibing.
All right. Okay. So it's great to hear the industry has really making a big efforts to reduce the CO2 emission. So very similar in academia, in universities, we're also making efforts to develop, for example, the solar energy, the technology, which would also serve to reduce the CO2 emission. So today, I would like to share with you some recent findings in my research group at OIST on perovskite solar cell technology, which is a promising next generation solar technology. Okay, so first of all, I would like to really thank the efforts from my research units, as well as the strong funding support from my university, as well as the public funding from Kakenki. So first of all, I would like to share with you a beautiful campus view of OIST. So it is a very new university, it's still very fastly developing. As you can see, there are already several lab buildings, and we are about to see even more buildings in the near future. Another important thing I would like to mention is the OIST is situated in Okinawa. As you can see, the campus is very close to the ocean. So for everyone working at OIST, they have the privilege from many corners of the campus, they can see beautiful ocean views. And I would say the ocean has become a very, very important, vital element for people living in Okinawa, and assume it's very similar for many other places close to ocean, including Hawaii. And it's even more so, I would say, important for the ocean species, plants and animals, those fishes. So ocean plays a tremendously important role for the very high biodiversity of the ecosystem in Okinawa. And one of the very important contributing factor to this biodiversity is a coral reef. On the other hand, there's unfortunate news. If you look at a couple years ago, the Guardian says that 70% of the ocean region close to Okinawa had been really damaged by a phenomenon known as bleaching. And it is clearly has this coral bleaching behavior, the phenomena is related to the water increase temperature. And so this relates back to really today's main theme, the climate change, the global warming. And this is where we start to look at the ways to reduce such negative impact. So in my lab, we are mainly emphasizing the research on the novel low-cost, high-efficiency solar cells, and this to harvest solar energy the clean, sustainable way. And also, we try to store this energy, the lithium-ion batteries, and also try to develop even more efficient LED lightings. And altogether, our hope, our goal is to achieve so-called zero net energy building that will be fully self-sustainable and with zero CO2 emission. So in our lab, I just want to give you a little bit of glimpse how we do that. And many times, the materials play a very important role. for the solar cell devices. So the first step in our lab, we would like to really study the material itself. And many times, if you can understand the structures of material and correlate with their properties, and then you can develop very efficient devices. So with really advanced characterization surface science tools in our lab, we can get to know very high resolution, very detailed information about the various different functional materials, energy materials. And then we'll go one step further, try to fabricate some proof of concept energy devices in our lab. And hopefully in the end, we'll try to have this feedback loop between fundamental basic science as well as real life energy devices. So why perovskite solar cells are interesting and attracting lots of attention? And for any solar cell technology, there are important 3 parameters we should consider. That is fabrication cost, efficiency, and lifetime. If we look at these 3 important parameters, perovskite solar cells have really gained much of the momentum and achievements in the past, a little bit slightly over 10 years. So Miyasaka sensei in Japan was the first one utilizing this material in solar cell in 2009. And at that time, the efficiency was below 4%, but with only 11 years, nowadays, the highest efficiency already achieving is 25.5%, which is very close to state-of-the-art single junction crystalline silicon cells. The best cells on the market you can obtain is about 22-23%. And if you look at the cost, so perovskite solar cells is even easier and cheaper to make. So this is mainly because the raw materials are low cost, and also the process for making perovskite solar cells are usually low temperature, doesn't require lots of the capital investment on the equipment, and doesn't require really sophisticated heating process, energy intensive processes. And overall, all these factors lead to the relatively low fabrication cost for perovskite solar cells. Nevertheless, the lifetime was once a really leading challenge for the perovskite solar cells. And but we are very, very happy to see over the past 4 or 5 years, many research groups in the world, including ours, have made lots of the progress in this direction. And we have already been seeing increasing lifetime and for perovskite solar cells. So in the next, I would like to show a couple of examples to give you a little bit of flavor what we do in our lab. How can we advance from the basic science and make a connection to the real life devices? So first example was focused on the atomic resolution, real space, atomic arrangements we observed on the perovskite materials. So this is in collaboration with Professor Nangyu Park in Korea, and also the calculation theory support from Professor Lee in China. So this was the first work to really realize the atomic resolution imaging to see all these atoms, ions, and also cations on the surface of perovskite. So once you understand these spatial arrangement of these atoms and ions, then you can correlate with their structures. And this is what we kind of find. And also a particular point from this study is that we did find, although many places are very high quality, but there are certain places consisting of these dark spots, and which represents the defects. Okay, and for devices, especially solar cells devices, to working efficiently, and it's very important for us to reduce the number of the defects and to achieve even higher performance. So this is what we did in the next study. So we try to analyze the various different important interfaces in perovskite solar cells And for each of the interface, we find the optimization and necessary procedures to reduce the defects and increase their quality. And indeed, the influence of these strategies is significant. So we were able to fabricate 5 centimeter by 5 centimeter perovskite solar modules. And on the right-hand side, I show you the influence of these interface engineering technology. So without any surface engineering, you can have the efficiency around 13%, or with some amount of the interface engineering, you can see the increase, the starting efficiency without any engineering interface optimization is 11%. But after some partial interface engineering, you reach about 13%. If you really taking into account all the relevant interfaces for perovskite solar modules, in this case, we can really achieve 16.6%. So there's obvious performance increase when you introduce these interface optimizations. So for a solar cell to make a big impact, it's not only the efficiency, but also its lifetime. That is, it matters for a solar cell to working at its peak or high efficiency for how long time, right? So we also studied these lifetime and stability properties of perovskite solar cells, solar modules in our lab. So the top figure shows that without these interface optimization, perovskite solar cells relatively degrade very fast. And only after maybe 300 hours, it already reached the below 80% of its peak performance. On the other hand, if you really do the interface optimization, you can really get very high lifetime. And if you even add one more protection layer, which we call encapsulation for perovskite solar module devices, we can even enhance. Here we say, we measured T80 lifetime, and the T80 lifetime is essentially the performance drops at 80% of its peak efficiency, and this lifetime, T80 lifetime, can really be 2,800 hours. And if you really translate it into the 8 hours or 9 hours per day operation, it's about 1.5 years. So we are not really, seeing 10 years, 20 years stability yet, but it's very promising. We are moving towards the right direction. I think with that, I have already finished my presentation, and thank you very much.
Yabing, thank you for that excellent presentation. So we've heard from 3 excellent panelists today, Christine Gamble from CarbonCure, who talked to us about carbon capture and also utilization in the concrete industry. We heard from Shimrit of eConcrete, who talked to us about carbon sequestration through the support of marine environments, and also that can be very helpful for the built environment in adapting to climate change. And then we just heard from Yabing, who talked to us about the next generation solar cells. So what I like to do is, first of all, thank you for all the excellent questions. Please keep them coming and input them into the Q&A ideally, so we can continue to keep track of them. We did see some questions in the chat, just as a heads up for Naoki, and then also for David. But before we go to those questions, I just have one round of lightning fast questions for each of our panelists, just to get the party started. So the first question is actually going to be for Christy. And the question is, if you could please describe examples of US policies relating to building with CO2 mineralized concrete and reducing embodied carbon in the built environment, including the resolution from City and County of Honolulu, and also what difference do these types of policies make?
Well, thanks, Veronica, and happy to get the party started, as you said. It actually looks like there's a question in the chat panel as well that was anticipating this, asking if government can help to create policies to add carbon to concrete. So there is, generally speaking, a growing movement among policymakers to address embodied carbon in infrastructure, and specifically the carbon footprint of concrete. Now, a big reason for this is because government agencies procure about 40% of the world's concrete. So a lot of concrete is going to things like paving on roadways and lampposts and sidewalks. A lot of sidewalks are being built with concrete. So as a result of that, government agencies, whether they are federal, state, municipal, are undergoing all sorts of policy to figure out how to procure better. And example of that policy, the city of Honolulu happened to be one of the first to enact policy in this space. So Resolution 18283 was put forward in 2019, and it's resolution that supports the use of CO2 mineralized concrete in City of Honolulu projects. So this is a very direct example of the city putting forth a policy that directly encourages local industry to utilize CO2 as part of its concrete. There's other policy that's being put forward that addresses this in different ways. One policy that I'm particularly fond of is called LECLA, which stands for Low Embodied Carbon and Concrete Leadership Act. This was first introduced in New York State legislature and is being, we're seeing it being introduced in a number of other locations as well. And what it does is it's a bit more technology agnostic and creates incentives for concrete producers to, first of all, disclose their carbon impact so that there are tangible measurements that can be made of how much carbon was emitted in the creation of this concrete. And then secondly, to utilize novel sustainable solutions, including CO2 utilization technologies and other types of sustainable innovations to reduce that impact. And in fact, it gives procurement advantages in the competitive pricing bidding structure that exists within every type of procurement industry. That's one example. Another one is the city of Portland has a low carbon and concrete procurement strategy for its various sidewalks and city applications that on a similar structure simply asks for transparency to understand what the carbon impact of concrete is, and then creates ceilings for the amount of carbon that is acceptable for city procurement. So a lot of different types of policy that is in place. Most importantly, from my perspective, the most effective policy is policy that addresses procurement directly. There's been a lot of exploration of policy that talks about carbon capture, but as I alluded to in my presentation, capture in itself is only part one of the solution. The second part is what do you do with that carbon once it's captured? And so that's where procurement, which has such a tangible impact because of just the sheer volume of procurement that exists in government, specifically as it relates to concrete, can have the most tangible, real impact.
Great, thank you, Christy. Thank you. Okay, next question is for Shimrit. Shimrit, what would support the use of coastal and marine infrastructure such as yours? And maybe you can discuss some of the barriers that you encounter and how you go about addressing them.
Absolutely, and this would link perfectly to the question that Christy just answered, because one of the main hurdles at the moment is lack of incentives and lack of policies that actually require for mitigation, for on-site mitigation, and for construction of projects that actually take nature into consideration. So today, for example, if you decide to build a new infrastructure project or even expand an existing project, like a port or a marina in Hawaii, let's say, obviously nobody's going to be planning that on top of the most pristine natural reef that's out there. And there's going to be a lot of efforts to try and avoid loss of natural habitats. But let's say once an engineering decision has been made to position a new infrastructure or to extend it, at the moment, there's really literally no policies as to how to build it. So it might not be directly on the ecosystem that we want to preserve, but at the moment we're building these kind of blank concrete canvases in the water that, if anything, inflict negative impacts on the marine environment. And if we had policies that are pro-environment, that are talking about nature-inclusive designs, then the procurement process will actually have to look at all aspects of the value chain, starting from the concrete itself and the design and the admix to make it much more in tune with nature. So I think that's one of the major barriers. And as I mentioned in my presentation, actually in the US at the moment, and I'm checking these policies across the globe with our activity, the US has the most environmental policies that are proactive in place because of mitigation banking. And we have been able to offset some of the mitigation penalties with our technology. But in Europe, for example, there's no mitigation banking, and not even in all of the US states, there's mitigation banking. So we need to strengthen the policies. And I think the other thing is knowledge. And that's why I'm so happy to be here today and to speak to you, because not everybody knows that this is a huge problem. I think that a lot of the people that look at the ocean environment and even look at the climate impacts and climate crisis think about ocean acidification and think about plastic pollution and ways to really reduce the carbon footprint. But the concept of us building miles and miles of infrastructure and protections on top of living habitats and not really trying to mitigate that, that's something that's not at the focus at the moment. And that's something that I'm fighting personally. I'm trying to raise awareness. On a positive note, I see a lot of acceptance, and that's also answering one of the questions in the Q&A. We are already engaged with multiple ports, the Port of San Diego, the Port of Rotterdam, the Port of Hamburg. We're now going into a project with the Port of Vigo in Spain that are looking for environmentally sensitive technologies. We're engaged with stakeholders like the offshore wind developers that want to do a scar protection that's also in tune with nature in a nature inclusive design. So we're seeing a lot of interest, but there's still so much work to do, especially in developing developing countries and in small island communities that are really vulnerable and faced with threats of sea level rise and extreme weather events. And these communities are the most in tune and in touch with the marine nature. So it kind of makes a natural place for e-concrete.
Thank you. Yes, and by the way, you're an excellent advocate. I learned about you through the We Empower Challenge, WIRE, Women in Renewable Energy here in Hawaii. We are a partner of that UN-led initiative. And Amanda Ellis from the Isla Center and ASU has been just a huge driving force. So thank you for all your hard work and efforts. Next question is for Yabing. And Yabing, Dennis Teranishi had the same question I was about to ask you, which is, when can we expect these new solar cells to become commercially available?
So as I mentioned in my presentation, right now, the efficiency is very promising, already reached 25.5% and close to even the best, silicon solar cells, which is still the market dominating technology. And but I should also mention that such efficiency is right now only achieved for relatively small size cells. We call lab size cells. And so I think the most relevant thing to ask, how we can really mass production and make also upscaling of these small sizes. So this is the number one, I think, important factor that will determine how to commercialize the perovskite solar cell technology. And secondly, as I mentioned, right now, the lifetime and also stability issues are being resolved with better strategies, but obviously, if we can even achieve longer lifetime, it will be even more beneficial. So with these two things resolved, we are quite optimistic. The perovskite solar cell technology might have really a strong appearance in the commercial solar cell market soon in the next 5 years or so. And the other factors I might say, which might promote the perovskite solar cell R&D, is whether there will be active participation from the industry, because it's not surprising. Maybe the industry, those companies which have been heavily investing and also research on the other solar technologies might already find some very promising techniques to increase their, for example, the lifetime stability, and also for the scalable fabrication. And these technologies or techniques might be optimized and modified if necessary and applied to perovskite solar cells. Then we'll see much faster progress in this direction.
Thank you, Yibing. Really appreciate the great work that you're doing and excited to see these perovskite solar cells come to fruition commercially. I'd like to turn it over to David James, who's been monitoring the chat, the Q&A, and has some questions from the audience to the panelists. So take it away, David.
Thank you so much. And we do have a number of really good questions, but invite the audience to continue to ask questions. And let me, Yibing, since I have you here, I just finished an answer. Let me just follow up. There is another question to you. What is your stand in placing perovskite solar cells on top of water and on land? Any particular thoughts about that?
That's a very excellent question. For perovskite solar cells, I think, like also other solar cells, to work in the best condition with a high efficiency performance, I think both things are important. That is high efficiency and also the high stability. And with that perspective, I would say probably land is a much better choice. Because if you put that on ocean and ocean weather, the local weather is hard to predict, and maybe it will influence the performance of perovskite solar cell. And also the ocean, also the moisture and containing the salt might kind of serve as a corrosion factor for perovskite solar cells. So with that kind of understanding, I would say probably land deployment of perovskite solar cells will be more suitable.
Thank you so much. Next question is for, I think, both Christy and Shimrit. And it's actually, I'm going to combine two questions here. The first one is, do the owners of any particular place that's using to build something in concrete, do they have to specify the use of the type of concrete, for instance, that CarbonCure is creating? Or are the concrete producers using it to make all of their concrete, regardless of whether it's requested? And just I'm tying that into another question that was in the chat, specifically related to Hawaii. Are all the concrete makers in Hawaii adding carbon to their products? So Christy, could I turn that to you first?
Sure. Well, first of all, in response to, do owners need to specify it? Need to specify it? No. Can owners specify it? Yes. And that can really help to drive it. So how it works is a CarbonCure partner will use CarbonCure on all applications where it's permitted within the specifications. There are a number of kinds of concrete specifications that use what's called a prescriptive spec, which means it requires a lot of very prescriptive criteria for how the concrete is being delivered. This can act as a barrier. So a concrete producer might propose the use of CarbonCure or other innovations to reduce the carbon footprint, improve the performance of concrete in a project, and they can run into barriers from the specifications. Now, often they're able to overcome that, but an owner, a designer, can proactively overcome that and adjust the specifications to be more conducive to sustainable innovations. They can also, as an owner, require or request the use of CarbonCure or other kinds of innovations as well to really accelerate that adoption and ensure that the concrete that's being procured at that particular construction site is the most sustainable option available. So the answer to both is yes. And David, what was the second part of that question?
Particularly in regard to Hawaii, are all the concrete producers in Hawaii doing this?
We are working with Island Ready Mix and HC&D Concrete in Hawaii. We do hope to be working with all producers on the islands in the near future.
Great, thanks so much. Shimra, did you have any particular comments on the first part of that question? In your case, do you find that a number of people are requesting to use the kind of materials you're producing?
Yeah. So with us, it's less of the private, let's say, developers or a private home can request if they have a seawall. Like now we have a couple of projects in Miami, and the actual owner of the seawall is requesting and has every right to specify e-concrete into his or hers property. But that's a small part of our market is private. And when we're talking about ports, city waterfronts, marinas, these are things that typically go out to bid. And in that case, the technical specification will have to include nature inclusive designs, bioenhancing concrete, e-concrete. I mean, that's something that has to adhere from the very early stages of the design of the project into the bid documents so that eventually it will be in the project. That's one of our challenges. If it's not in the spec, even if we give the product for free, it's just not going to be in the project. So that's why we have a lot of education, and the life cycle of these projects is very long. But we're seeing a lot more open-mindedness and acceptance to the technology, and starting to see bids coming up in different places that we've never even been to that specify concrete, which is great.
That's really great. Thank you so much for that. There's a question here that I'll open to the floor to see who might have an answer. The question is, I have heard about blue, green, and other colors of hydrogen. What do these mean, and how should they be evaluated and pursued to ensure that we can achieve our climate change goals? Anyone in particular feel they have the ability to jump on that? Yabing?
David, are you talking about the hydrogen technology or?
Hydrogen technology.
Well, I only have limited research experience on hydrogen. So the basic idea is it's a very clean, and I also heard very high density of the fuels for many purposes. So I think some automobile company are really investing lots of the funding to research whether it's possible for the hydrogen-powered cars. And from that perspective, it might be a possible technology to help also reduce the CO2 emission, because obviously automobiles nowadays, using the gasolines and will emit CO2 as well.
Great, thank you so much for that. There's a very interesting question that's come in for both CarbonCure and eConcrete, and I'll just read it directly here, and then maybe Shimrit, I'll turn it to you first. For CarbonCure and eConcrete, you've nodded to direct air capture technologies as being part of the solution in climate mitigation and regeneration. ASU has developed the world's first mechanical trees from Klaus Lackner's Center for Negative Carbon Emissions. Could this carbon drawdown model be used in your concrete technologies as sequestration solution? I'm not sure if you're familiar with that or not, but if you are, Shimrit, maybe I'll turn it to you, and if not, Christy, but if neither of you are familiar with it, we can follow up later.
Well, I'm not familiar with it. I'll just tell you that our approach to innovation is to try and combine and mix technologies. So I'll be very happy to explore this, but I don't have any specific knowledge on that program.
And there is the individual who wrote about this did put a link in the chat, which might be interesting. So we'll try to find out how that might relate. There's also a question or a statement here that in Hawaii, the state legislature requires the use of mineralized concrete in state buildings. I guess it's State Bill 161. Do any other states in the United States or any other places that you're familiar with have particular bills that are requiring the use of mineralized concrete? Christy, maybe you could comment on that.
Sure, and also just on the CO2 source from Arizona, this sounds really exciting, and If the net result is purified CO2, then, absolutely, in theory, it's something that could be utilized in CarbonCure's application. And so we're exploring all kinds of options for utilizing CO2 regardless of source, provided it meets our engineering requirements. With regards to SB 161, so this bill specifically, as it's written, it requires all state building construction that uses concrete to use post-industrial carbon dioxide mineralized concrete unless the use of materials increase costs or delay construction. So this is really, it's a really fantastic bill that encourages, obviously, the use of CO2 utilized concrete. This particular bill is unique to Hawaii. It's possible in Hawaii because of the landscape and the various partnerships with concrete producers. We are seeing similar types of legislation in other states, but in other states tends to have different nuances to the language to perhaps include other kinds of innovations. And in many other states, there are many more concrete producers within a region. And so we're not as advanced in terms of our market penetration as we are in Hawaii. And so it's just, Hawaii is at the very forefront of this. And it's wonderful to see this kind of leadership being displayed by the state.
Well, thank you so much for that, Christy. And let me just express my appreciation to Christy, Yabing, and Shimrit for being here today, and for everyone in the audience for taking some time to write in some questions. We also received some really good links in the chat that I hope everyone has a chance to look at. Let me turn it now over to Veronica for final words and comments.
Thank you, David. And I echo your words. I'm so appreciative of having Christy, Shimrit, and Yabing present and share their knowledge with us today. Also, thank you, David, for being our excellent co-host, and Aoki, our excellent DJ. To wrap up, I would like to ask everybody in the audience to please enter into the chat your #1 takeaway from today. In terms of what is next, this video recording and the presentations that you saw today are going to be made available. We will be sending an email through PICHTR's email address that will provide you information on how to access the video recording as well as the presentations. And I'm going to ask Naoki if you can please put into the chat the survey. It's a 3-minute survey on today's webinar. We ask if you can just take a few minutes to complete that. It helps us to figure out how best to improve our webinars, what topics you would like to hear about in the future. So if you could please complete this 3-minute survey, we would very much appreciate it. Our next webinar, please stay tuned. It's going to be held on March 10th at 12 to 1:30 p.m. Hawaii Standard Time. The topic is going to be on climate change resilience planning and adaptation. Last but not least, I would like to encourage everyone to please get in touch. Here's information on PICHTR, but also on the OIST Foundation. I also noticed that our presenters on their presentations also had contact information. So please reach out and always open to exploring opportunities for collaboration. So with that, thanks everybody. Really appreciate your time, your attention, your questions. And with that, we are Pau, mahalo, and thank everyone. Take care. Bye.